O'clock, so welcome to the last physics seminar of the fall semester 2025. Today we have a talk about maybe applied physics. You know, we have lots of talks about mechanics and electricity and magnetism, but hardly ever about the fun stuff where there's a lot of physics, but we really do something with it. It's not for the physics sake itself. So Professor Scruggs is in the Department of Geology here at Wichita State and works in geology, geophysics, and she's going to tell us today about estimates of condensed water in the Hunga volcano, Plume. And so you got your undergraduate degree in Kansas City, then spent a bunch of years in California, got your PhD at Santa Barbara, and are back here at the central United States, where we have a lot of geology, but no volcanoes. So, all right, help me welcome Melissa Scruggs.
Right. Thank you so very much. Well, I first need to clear the air. I dabble in geophysics. I dabble. Okay, I'm an igneous petrologist and volcanologist, and what that means is I study the physico-chemical processes that result in different compositions of lavas and try to understand what happens inside of a magma chamber to make a volcano erupt. So that's my background. This project kind of came out of a postdoc I did. This is an idea I had during my postdoc work, and this is just an additional project that ended up spawning out of it. And as a volcanologist, when this eruption occurred, this was just insane. Like, this was just so cool. And hopefully, by the time we're done, I'll have convinced you that the phenomenon that this volcanic eruption produced have not been seen since Krakatoa erupted in 1883. Yeah. And this volcano erupted in 2022, so just a few years ago. This is Hunga volcano. HTHH stands for Hunga Tonga Hunga Hapai, and I'll show you what I mean. But first off, we'll ask what the question is, what is a volcano? Because a volcano comes in many different flavors. It doesn't always look like the nice conical picture you see up here, right? A volcano can simply be a hole in the ground. There's these types of volcanoes called MARS, M-A-A-R-S, where you just have magma interacting with groundwater and then just from below. That's it. Definitely not your stereotypical volcano. So we're going to be talking about a type of eruption that's not a stereotypical eruption, but it is at an active volcano. And just because you guys probably will never hear this again, an active volcano means that it has erupted within the last 10,000 years, or if it has not, then we have evidence for an active magmatic system beneath it. So the closest active volcano to here is actually in Colorado. It's called Dotsero Crater. It's one of those underground explosion craters, and it's still considered active because it technically fits this definition of 10,000 years. And there's no real typical volcanic eruption either. They come, again, in all flavors. We've got things from nice passive eruptions of Kilauea that are a VEI 0. This is measured on the Volcano Explosivity Index. Or we have the 1980 eruption of Mount St. Helens, which was a VEI 5. Or Yellowstone, up here, the super volcano Yellowstone. The big caldera-forming eruption that occurred, 0.6 million years ago was VEI 8. And by the way, that's the 21st most dangerous volcano in the United States. There's 20 that are more hazardous than Yellowstone, and my grad students are working on one of them. So just to plug them. All right, now that I've done that damage. So we've got our regular Kilauea-style eruptions, but there are more, right? There's more types of eruptions, and I want to show you one that happens when you get water involved, right? This is called a phreatic explosion. This example occurred in July of 2024. This is in Biscuit Basin in Yellowstone.
Shit. Run, run, run.
Now notice there's just a little bit of dark here. Everything you're really seeing is steam. There's no fresh magma involved. This is not a true eruption. This is just a volcanic explosion where a little bit of groundwater gets trapped somewhere in the system and can't make the normal phase change that it wants to, gets under so much pressure, but then can make that phase change and an explosion occurs. Right, so this is called a phreatic explosion. Nobody was seriously injured in this, thankfully. And then if you add magma and water together, we get a phreatomagmatic eruption. So this is a true eruption. We have fresh magma involved, and there's lots of different types. I really like this diagram because it shows the many different places within a volcanic edifice or the body of a volcano that you can get these types of eruptions. For example, this is Tongariro in New Zealand, and it erupted out the side when magma came into contact with its hydrothermal system. Or Mount Ontake in Japan had a summit crater, a phreatic eruption that had PDC clouds boil out of the side of it. Anywhere where you can have magma, which as you can imagine is very, very hot, basaltic magma, the kind that erupts out of Kilauea, is going to be about 1150 C, 2400 Fahrenheit. The magmas we're going to be talking about today are probably around like 975, 1000 C, so 2100-ish. I'm not good at the Fahrenheit when it comes to magma temperatures, admittedly. All right. But not all underwater explosions are the same, right? Just because you put magma and water together into contact doesn't mean you're going to get a violent eruption. In fact, whoops, sorry. Come on, there we go. Maybe this one will play later. But in fact, you can see over here, that is not as explosive, right? So what's the difference? Both of these eruptions take place underwater, but we have very, very different measures of explosivity here. Well, it depends on a couple different factors. The first is the amount of water that's actually involved in the eruption. So this is a plot from Sheridan and Woletz. On the x-axis, this is the mass, like the fraction or proportion of water that's involved in the eruption. If you have less than a 1-to-1 ratio, we consider it a dry eruption. If it's greater than 1-to-1, it's a wet eruption. And then over here, we have what's called MORB. MORB is geologist acronym for Mid-Oceanic Ridge Basalt. And this is our underwater, very, very wet volcanism. In fact, 80% of all of the volcanism that occurs at any given point on the planet is this style. And we don't even think about it, right? It's very passive, not hazardous at all, right? But if you allow the magma and water to actually come into contact, you can get some explosivity. I'm getting a little ahead of myself. Right about here, when you have about 30% water, this is the maximum efficiency of explosivity that you can involve in a phreatomagmatic eruption. So keep this in mind, because we're going to be talking about some really cool big explosions today. We want to make sure we're right in this sweet spot, but anywhere up here is pretty good. All right. As I'm sure you could see I was alluding to, right here we have creation of a steam layer, right? So the Leidenfrost effect really controls whether or not that magma can come into contact with the water. If you have very slow rates of extrusion or lava coming out, then you've got plenty of time to build up that steam layer and prevent the magma from coming into contact. But sometimes if things happen fast enough or rapidly enough, that film layer can collapse. And when that film layer collapses and the magma can come into contact with the water, you can have a very efficient, very rapid heat transfer. And then magma fragments also, once it quenches, magma will fragment. These are some photos from Gonerman that just kind of show how magma will fragment. You can kind of see the patterns. It stretches out. As it expands, it will burst. And so like volcanic ash is really, I'm sorry on Zoom if you can't see this. It's very pointy, You've got kind of bubble wall shards where things have exploded, and it's a liquid. It is a silicate melt. So this is a rock, this is glass that you're seeing. It's just currently molten and hasn't yet solidified. Right. The next thing that controls how explosive a volcanic eruption is the depth to a vent. So let's say that you do have magma and water coming into contact. Let's say that you do have things happening fast. Let's say that you're not at a nice, relaxing, morb, mid-oceanic ridge eruption. But how deep the vent is matters quite a bit. Havre Volcano is in New Zealand, I believe. And it is very similar. Yeah, so this is Santorini in Greece, all underwater volcanoes. The question is how deep is the vent? So at Havre, the depth to the vent is 900 meters. That vent is currently experiencing about 8 to 9 megapascals of pressure. Deeper in the caldera, when you're at what, 1,500 meters, it's under about 15 megapascals of pressure. Shallower vents, only 2 megapascals. You can imagine that if you have a very explosive eruption, the greater the amount of overpressure on the vent from the water, the less able that eruption will be able to breach the surface of the ocean, right? So in fact, with Havre, we had pumice rafts because the eruption plume wasn't able to breach the water, or at least wasn't recorded to have breached the water. But pumice rafts were recorded that floated across the Pacific. And that's how we had known that this had a very explosive eruption, even though the vent's very, very deep. All right. So that brings us to our remote volcanic island in the Kingdom of Tonga. This occurred in 2022. So Tonga is a country, it's an island country, an island nation. Gosh, over 30 different islands, but many of them, thankfully, are uninhabited. It's located along the Tonga-Kermadec Trench, north of New Zealand. And so volcanism occurs here because you have one plate, the Pacific plate, subducting here underneath the Indo-Australian plate. When you get one plate subducting underneath another, you have a way to create magma beneath the plates. And that magma can then rise up and produce volcanoes about 100 kilometers inland from the trench. This is a very notable pattern we see at volcanic arcs around the world. All right. So this star is Hunga Volcano. This large island, if you can see it here, is the island of Tongatapu. Nuku'alofa is the capital of the Kingdom of Tonga, and it resides on the big island. This is where most of the people live. There are some smaller communities on the outlying islands. Most notably up in here was an island called Mango Island, where one of the people did perish, but other communities did, people did survive miraculously. As you'll understand why I say that once you guys see what happened. So Hunga Volcano is about 67 kilometers away from the main island. This white dot right here, that is Nuku'alofa, the capital. Okay, so this is our volcano. This is Hunga Tonga. This is Hunga Ha'apai. And it doesn't look like much. It looks like, it's just a couple islands hanging out in the middle of the ocean. But what you're not seeing is underneath. You're not seeing the whole volcano. This is the very, very tippy top of a massive volcano that extends all the way to the ocean floor. Yeah, it's big. You're just not seeing the whole volcano. All right. This is the caldera of it. It last had its big caldera forming eruption about 1,000 years ago. Since then, the first recorded by a white man eruption was in 1912. I have to say that. Was in 1912. But also, this is a remote volcanic island out in the middle of the Pacific. So there probably were a lot of eruptions that just never got recorded by anybody, to be honest. So we have eruptions in 1912 and 1937, then some pauses until the late 80s. Things start to pick up in the early 2000s when we have an eruption in 2009, and then another eruption in 2014 to 2015. And this eruption, the 2014 to 2015 eruption, was notable because that's when this island was first discovered. Whoops, this little cone. And it was first studied in 2016 as a kind of a revegetation experiment, just to observe how do newly created landforms weather, how does vegetation take place, are there animals on them? Because this is a brand new island, and so it's a great natural laboratory to observe natural processes. Alrighty. And you'll notice that the vents kind of dance around too. So the early 20th century, so in kind of the south end of the caldera, and then the early 21st century eruptions in the north side of the caldera. Alrighty. This is a resurgent cone of a caldera. So what that means is this caldera formed about 1,000 years ago, and then 1,000 years of magmatism and eruptions build up this cone in the center. There's a lot of places in the United States alone where you see these resurgent cones, and as a volcanologist, that's a big key as to, hey, there's still active magmatism here. All right. In 2015, it exhibited Surtsayan style eruptions. Surtsayan eruptions are not super duper explosive, but they'll still hurt you. You don't want to be in the area for sure. And this is kind of what they look like. These gray black clouds, that's fresh magma and water. And then you can see the steam plume rising up as well. The current eruption that we'll be talking about today began back in December 20th of 2021. And I know that you might think, okay, well, you've got a lot of eruptions up here. But a single eruption, well, if the January 14th and 15th eruptions here, since there was no apparent activity about the week before, if those were to be considered a new eruption, this break in time would need to be at least 90 days. If you don't have a break of 90 days or more between eruptions, then that's considered the same eruption. So that's why even though we have a little break and the activity starts, about a month prior on December 20th, this is all still considered one eruption. But that tells us something. That tells us that the system is very unstable. You've got a month of explosions and eruptions that are really disabling the system. Think about it like this. When have you ever just had just the gnarliest stomach bug, right? Now imagine having that stomach bug for a month. Your system is going to be in even worse shape after a month of that, right? I like to say that volcanic plumbing systems are kind of like human plumbing systems because we deal both with pressure and gases in both humans and volcanoes. All right. So the day before the cataclysmic eruption, cataclysmic, I'm sure you can imagine, horrible, big word, very dangerous sounding, right? So the day before, on January 14th, we had a very significant eruption at Hunga Volcano, a Plinian eruption named for Pliny the Elder, who observed Vesuvius. Very explosive. This plume went up 20 kilometers, right? So very, very tall plume. And this is, in and of itself, a notable explosive eruption. But the next day just knocks everything out of the park. So this photo was taken by satellites on November 17th, 2021. This is before the eruption begins. You can see here we still have the 2014 to 2015 cone connecting Hunga Tonga up top and then Hunga Ha'apai down here. This photo was taken December 30th of 2021, so now we're a few weeks into the eruption, about halfway through the sequence. You can see the Surtsayan eruption cloud, eruption plume, and we're actually growing this. By the time we've reached January 7th, we've doubled the size of this island, right? Our vents moved a little bit, but this cone has grown massively in just a few short weeks. Then this is the Plinian eruption on January 14th. These are scientists with the Tongan Geological Survey that took this photo. As you can see, we've got some nice lenticular clouds forming above the eruption plume. These are called coxcombs, like the kind of sand plumes with the magma and water. They look like rooster, like the head of a rooster, which is why they're called coxcombs. But very dangerous to be any closer than this, really. And honestly, if these guys were here the very next day, they would have died, being this far away. The next day produced some phenomenon that were just absolutely unreal. And I'm super excited to share them with you. So this photo was taken just 3 hours before the eruption, right? So day before, big Plinian eruption. And this eruption destroyed the whole center, that the vents moved. Without this photo, we would have had no definitive proof that the vent had been relocated to shallow, beneath the, just a few hundred meters beneath the surface of the ocean. Yeah, Nick.
Not that picture, but the other one you showed flashed out. Yeah, there. Is that a train of waves coming off of there? And is there some kind of seismic motion that's generating swells?
Probably, I mean, I would imagine there's probably some collapse in there. I have no doubt that those are waves caused by something moving that just happened to get caught. That in and of itself these waves in and of themselves are not a signal. So what I can tell you is that the eruption didn't start until several hours after this. Well, not the eruption, but the cataclysmic phase, the really, really big part of the eruption, it didn't start until a few hours after this photo was taken. But that doesn't mean that maybe some things weren't happening that didn't get recorded. And you'll see why, because there weren't any seismometers near enough. So I can't say no, but I can say that what was picked up didn't pick anything up until several hours after this was taken, if that makes sense. Good question. So without this photo, we would have no definitive proof. We would have had our thought, hypotheses, but this just was luck of the draw, which is really cool. All right. And this is our eruption. I love the jaw drops. Yeah.
So what's this cave? What's the diameter of this?
This was the Himawari 8 satellite. I don't know the scale other than this is the Himawari 8 satellite. This is like the whole. I don't know off the top of my head. Yeah, I don't know off the top of my head. Yes. We're getting there. Oh, we're getting there. Yeah, we're getting there. This is why I was so excited to give you guys this talk. We just submitted this for publication, a couple weeks ago. So I wanted to get things kind of wrapped up before I came over. 10 minutes.
10 minutes.
Yeah.
So you can see how far the curve is.
Mm-hmm.
Probably get an idea of scale beyond that.
Oh, we're getting there. We're getting there. This is a video. This video was taken by residents on the Big Island.
Oh.
Yeah.
So, check that out, man. That's the fucking volcano eruption.
So the plume's at least
Clouds.
70 kilometers. It's over this Big Island now.
All of that out. Oh, fuck!
And that's what it sounded like.
Fuck! Alu! Alu! Shit!
No, well, he's not, because when you hear that, you know that a tsunami is coming. And because the Kingdom of Tonga, because the people of Tonga were so well prepared, and because the eruption had already been ongoing, there was a tsunami warning the day prior. And so thankfully, everybody knew what to do, right? Luckily and surprisingly, as you know, from what the little you've just seen, only 7 people died, which is incredible, absolutely incredible. This is what is left over. So this is what was left over of the island after. We've got a little bitty scrap of Hunga Tonga up top, but Hunga Ha'apai survived for the most part. For the most part. But had we not had satellite footage of the island in 2015 and in this eruption, all of this would have gone undocumented, which is just really cool. Yeah.
That like sandbars right underneath the surface?
I would wager that's probably pumice and ash floating. Yeah, so we went from this to that in just a few weeks. It's pretty incredible. Yeah. This is stereo height reconstruction of the plume. So the Himawari 8 satellite footage and the GOES 17 footage were put together, and then NASA scientists were able to reconstruct the height of the plume. This was made from 10-minute increments. And as you can see at the very beginning, it went 58 kilometers. So this is the tallest recorded and reconstructed plume. So this went taller than the 1883 Krakatoa eruption plume did. This is taller than Toba. This is taller than any Yellowstone plume. This is the tallest plume that has ever been documented or reported or reconstructed, period. And it went over halfway to space, which is insane to think about. Also produced an obscene amount of lightning. Over 75% of all of the lightning on the planet in the most intense hour of the eruption was focused just over the volcano. There was a paper that came out on multi-phase turbulent flow in these lightning rings. So these lightning rings are caused by like ice particles and ash particles colliding as the plume is just roiling during the eruption. And this is just phenomenal. I got this off of a weather guy on Twitter, and so I was lucky enough to have wrote the first paper on this eruption by putting in some very long hours. And we were able to cobble together things like this video, the video that you saw prior with the kid and his sleeve, the sleeve from the shockwave, things like that. Earthquake records that were available and infrasound records that were available. And we pieced together a picture of the eruption that was, it's pretty good for some Twitter detective work. Also, I like being the first to publish because you can get the low bar. All right. So this was our paper, our seismic paper, and we published it because we did see a notable seismic signature. This is a teleseismic signature, and that's because, so Nick, you were talking about the seismic signature. The closest seismometer was, I think, 767 miles away in Fiji. There was no seismometer, even in the Kingdom of Tonga, to record the events of the volcano. So we don't have any near field or record of earthquakes very close from a seismometer very close to the eruption. Instead, we can use signals that are recorded on seismometers far away from the eruption. And this is called a teleseismic signal. It's a little weird to think about too, because when you're thinking about the seismic signature of a volcano, and I've got my little dancing volcano over here, whatever happens at the volcano shows up at as the opposite signal on the seismometer. So if something is coming up out of the volcano, like if you have an upward force at the volcano, it would look like a downward force at the seismometer. If you have a downward force at the volcano, it looks like an upwards force at the seismometer. And it's just because it's kind of pulling and like that, if you will. That was something that was really difficult for me to wrap my head around for my first time working with earthquake scientists. But we were able to find this very odd signature. So a downward force at the seismometer means an initial upwards force at the volcano. Our hypothesis is that there was magma that was maybe moving upward, and we kind of had a water hammer effect. We called it a magma hammer. I'm not entirely convinced of that, but we really couldn't come up with a better explanation. We still have yet to come up with a better explanation for this seismic signal. It was also heard in Alaska, audibly heard by people in Alaska. And then, yeah, I know. And not just, and this isn't just the infrasound recorded it in the audible range. Social media reports documented it. So people actually heard this in Alaska. Oh, that's a great question. 3:30 and 4 a.m. Alaska time. Okay, Alaska is, how many hours is Alaska behind Pacific? 3? Okay, so that would have been, the eruption would have started around 9 p.m. maybe the night before, I think, because I was on the West Coast and it was about 6 p.m. Mm-hmm. Yeah, I remember it was about 6 p.m. when I started seeing the first social media reports, and I was in Washington. And that was about 4 p.m. 4 or 5 p.m. Tonga-ish time. Yeah, that's a good question.
An hours, right? The speed of sound is around 340 meters per second, depending on temperature
and that, yeah. Yeah, and so this thing was moving at the speed of sound. It produced, that was my next slide. You asked about the pressure wave. So this, I assume in Hawaii, yeah, but there's a straight shot to Alaska, and I think because it's so far away, that's why it made the biggest to do, because it's that far, it's all the way in Alaska. I know it was also heard in New Zealand and Australia and close by, so cool. All right, and then here's our atmospheric pressure wave. So this is called a Lamb wave. It's an atmospheric boundary wave that propagates about at the speed of sound. And this eruption was so powerful that the Lamb wave circled the globe 3.5 times before it dissipated. Yeah, so this animation that Matt Barlow at Lowell made, it really shows the scale of the eruption. And again, what you're seeing, 7 people died, which is a miracle. So this also produced a new phenomenon I had never heard of called a meteotsunami. The Lamb wave in the atmosphere resonated with the energy that was put out into the ocean. So the energy of the eruption what we are hypothesizing is that it decoupled, and part of the energy went into the ocean, part of the energy went into the solid earth, and part of the energy went into the atmosphere. And so the energy that went into the ocean and coupled with the energy that was in the atmosphere, they both propagated about the speed of sound, and that resonance, which is called Proudman resonance, amplified the waves, creating what's called a meteotsunami. So a tsunami, but it's truly produced by the atmosphere. So this eruption was produced over in the Pacific. You can see here's our near field normal tsunami, and here's our meteotsunami. It's decoupled and it's following our Lamb wave. And it will in fact show up in other oceanic basins that are not connected to the Pacific, like over in the Caribbean, which blew my mind. I didn't even know that was possible. Yeah, travel times. So I think 5, there's 10, so 8 to 9 hours before it hits North America and South America. 4 of the 7 that passed away were women in Peru. Actually, there were a couple gals over in Peru that didn't get word of the tsunami, and so it was the Trans-Pacific tsunami that actually caused many of the deaths. Yeah, that's not an uncommon phenomenon. In 2004, with the Indian Ocean tsunami, over 200,000 people perished because we didn't have a tsunami warning system. People as far away as Africa died from something that happened from an earthquake that occurred in Indonesia. So. All right, and then here's the near field tsunami. So this is clips from a YouTube video Sam Purkis made. This was a paper in Science that talked about the 20-meter tsunami that hit the nearby islands. And so this is why, thankfully, many of them were not inhabited. And thankfully, the Tongan people knew what to do. This is also a really cool paper because he was able to use tidal gauges and the amount of windows that were broken from the pressure wave in the town to kind of constrain the explosive yield of these blasts that would have produced the tsunami. So the amount of energy that was put into the ocean to generate the tsunami, we're estimating at around anywhere, I think, a cumulative total of 24 megatons TNT. It also completely blew a hole in the top of the volcano, as one could imagine, right? So about 6.3 cubic kilometers of material were removed. That's based on Seabrook, but reports and estimates are kind of ranging between 6 and 7. But that's the total amount of material that was removed from the volcano. That's not necessarily the volume of fresh magma that was involved in the eruption. Also, because we're still not done with just the volcanic eruption yet. So that tsunami and the pyroclastic flows from when the eruption cloud came crashing down completely took out the internet for the country. So the country of Tonga was cut off from the outside world after about an hour. It took several weeks for communications to be reestablished. And this eruption put a quantifiable buttload of water into the atmosphere. And that's the subject of this study. So we'll talk about the amount of water that we're estimating was put into the eruption plume and compare it to other estimates that were made by other methods out there. We were also able to do some other really cool stuff. So this is a project I'm a co-author on. Again, this was kind of a morphed out of a postdoc, an informal postdoc I did and so the lead author on this is Steve McNutt. He worked for the Alaska Volcano Observatory, and then Earl Williams over at MIT, and my PhD advisor, Frank Spera. So we're a little motley crew. We use the explosive yield of this eruption that has been estimated by a couple different groups using a couple different methods. And we use magma steam calorimetry. So really basic intro chemistry lab. How much heat do you need to heat up this much water, to make the water increase in temperature? Basic, simple models. I'm a very simple geologist, and we love simple models, right? But we're able to use these methods to do some really cool stuff. We're able to estimate the amount of water that went into the eruption plume. We also were able to estimate the amount of magma that must have been involved to produce this big plume. And lastly, constrain magma storage depths. So how deep did the magma have to be and fragment at what depth in order to get up to 58 kilometers tall? So that's basically the project that I wanted to present to you today, but you got to have all the background first because this was just an insane eruption that produced some incredible phenomena that are allowing us to constrain these things using these methods. So the first step was to constrain the amount of water in the eruption plume, and to do that we used the stereoscopic imagery. It's elliptical. Again, cannot overemphasize, we are using very simplified models here. Very simple first order models, right? So yeah, this is about an ellipse. And we know the height from the height record. So we can estimate, okay, well, how tall was the plume? What's the approximate area of the umbrella? but that doesn't help us with the thickness of the plume, because the whole thing isn't going to be a plume, right? Well, we don't really have any good images because you couldn't get near enough. The shock wave would have killed you, right? So what can we do? We can use known eruptions like Mount Redoubt. So Steve McNutt worked at the Alaska Volcano Observatory when Redoubt erupted in 1990. And he was able to determine that, well, a lot of the time, an umbrella is about 1/4 the thickness of a plume. A lot of the time. Again, simple model, right? But as you'll see, the simple model doesn't work too badly, right? We're also estimating the radius of the core at about 15 kilometers. And I could not tell you why he picked that number. I genuinely could not tell you. If you've done a big collaborative project, you know that you work on your part and your co-author works on his part, et cetera, you know, and so this was Steve's part. I could not tell you why he picked 15. And we used 3 different models, so a couple different simplified plume structures, just a single umbrella, double umbrella, and a triple umbrella. But what's important is that in each one of these 3 models, we have the same thickness. The umbrella is always going to be 1/4 of the plume. It's just divided into different layers, and those different layers have different water concentrations. And those different water concentrations are constrained in a couple different ways. We're using the amount of water that's typically contained in a fresh juvenile magma, average thunderstorm over dry land, and the average thunderstorm over the ocean. Right? And because water gets incredibly concentrated in a plume's core, we're going to use some values that are even a little bit higher than that. So I've got some models up here, and again, to reiterate, the volume of all 3 is the same. The total volume of all 3 models is the same. The total thickness of the umbrella in all 3 models is the same. We're just varying the number of umbrellas and their water contents, like so, right? So using these values and these models, in model 1, we come up to 3 times 10 to the 12th kilograms of water in the plume, right? So a couple teragrams. We're on the order of teragrams, I think, is 10 to the 14, if I recall correctly. Model 2 is really large. Model 3 is my preferred model, but I think that a result in between Model 1 and Model 3 is probably the most realistic. Again, these are very, very simple models, and I've got my reasons for why I prefer Model 3. But regardless, if you compare the amount of water that would have been available in just the magma alone, just even the maximum amount of magma that could have come out of that eruption, the 6.5 cubic kilometers, if you will, out of the considering the normal amount of water that's in a magma, there's not enough. There's not enough water in a magma to have made the amount of water that should have been in the eruption plume. In fact, we need extra water. And so we're concluding that 80 to 90% of the eruption plume was not water derived from a magma, that it was additional seawater, which makes sense, and that's really logical. You've got an underwater volcano, and this vent is right beneath the surface, and you've got an abundant amount of seawater. Right? So that's not a hard reach. So in our study, in Model 1, we've got 3 times 10 to the 12th kilograms. Model 3 is about 8 times 10 to the 12th kilograms of seawater in the plume. And we also calculate the amount of magmatic water in the plume, and that's water that comes from the magma itself. This reconciles good on an order of magnitude scale with other studies. But it's also important to think about what we're looking at and considering. We are measuring, in our study, we're measuring the amount of condensed water, liquid vapor and ice crystals that are in the eruption plume. These studies that are an order of magnitude less, they're measuring vapor. So not necessarily the same thing. That's kind of an apples and oranges comparison. But, you know, vapor, it's still close. Using explosive yields, this Henley et al. Study has magmatic water only. In our study, we actually make the point, we very much disagree with the Henley study because they do not consider external seawater and their mechanism just doesn't hold up, in my opinion. Maston et al. Used magma steam calorimetry, and they got 3 times 10 to the 12 kilograms of water in their plume. And this is external seawater, I apologize. Using ash geochemistry and actually measuring the magma itself, the magmatic water, the water from the magma, not external seawater, would have been on the 10 to the 11th order of magnitude. So we're in the ballpark. We're in the ballpark. Next, we're going to figure out how much magma we need to use to heat up that much water, right? So how much magma must have been involved in order to vaporize this amount of seawater, turn it into steam, and put it up into the eruption plume. And this is where calorimetry becomes involved, right? So the isobaric heat capacity of basalt, and that's including both latent and sensible heat, is about 2,000 kilojoules per kilogram Kelvin. Water is about 4.2 kilojoule per kilogram Kelvin. Right? So this comes out to be about 10 times 10 to the 12th kilograms of magma. Accounting for the density, right? That comes out to be a little under 4 cubic kilometers of magma that must have been involved. And but that's assuming 100% efficiency, right? We know that that's not going to be a thing. So probably more. If we say, okay, well, maybe this process was 75% efficient. She has to go give a talk. Maybe this process was 75% efficient. That would require 5 cubic kilometers of magma, or even if it was less efficient. Maybe we can make 6 cubic kilometers work, right? But surprisingly, phreatomagmatic heat transfer is very efficient. In fact, the ash particles from this eruption were measured at 300 microns. Anything smaller than, 2 millimeters can be up to 99% efficient when it comes to heat transfer. So a smaller magma body isn't necessarily precluded. But there's other reasons why I don't think that the magma volume was 4 or less. I think that this was probably a 75, 60% efficient process because you have to think about all that energy that went into the atmosphere, all the energy that went into the ocean, right? We're not even close to 100% efficient here. All right. Next, we're going to reconcile with the explosive yields, right? So we're going to use the explosive yields that were measured by tide gauges, by pressure barometers that measured the land wave and everything, to try to figure out, okay, well, is this a reasonable volume of magma? And where was this magma stored at immediately before it erupted? Right. So for reference, we've got Ivy Mike, here's Little Boy and Fat Man. These guys are kilotons of TNT. Tsar Bomba is the largest human-made nuclear bomb, and that was at 50 megatons of TNT. And we are not on the human scale. This is why I love our planet, because those aren't even close. We are on the 200 megaton TNT scale. That's where we're going. Yeah. So the explosive yields that were measured to create the tsunamis, those range anywhere between 18 to 20 megatons TNT. The land wave, those estimates go between 61 to 200, depending on what study you look at and how they measured it, and also when it came out. The first one that's 61, that was like a month after the eruption. The later studies that had a bit more time, those are more up on the 100 to 200 megaton TNT scale. So this is a very powerful eruption. We're using classical detonation theory modified for a phreatomagmatic mixture. So we're going to take different proportions of water and mix them with our magma to see, okay, well, how much water might have been involved in this? Is it really 80 to 90%? Here, this parameter modifies, this is fluid and magma, so this is kind of our fraction of fluid here. This parameter is our specific heat capacity parameter, and this is our modified density parameter. And this is our modified equation. So you can see that it accounts for the mixture of fluid and magma particles in those different proportions, as well as the adjusted density and the adjusted specific heat capacity. Okay. All right. So we ran some models, and I'll go right here. These models are going to be isobaric. So we've got two, one run at 30 megapascal and one at 50 megapascal. The ambient pressure at the vent, let's assume that it's 150 meters below the surface, right? That's about 1.5 megapascal. So using this ratio, P vent to P naught, we can kind of estimate where P naught is. And P naught is where is the magma immediately before it comes up. This is our depth to the magma reservoir parameter. So if our model at 30 megapascals would jive, then that means that our magma was probably 1.3 kilometers beneath the summit of the volcano at the time of a big eruption. As you can see, that's not quite enough, even with a very large volume of magma. But if we bring our magma body a little bit deeper, right, have it stored, say, at maybe 2 kilometers depth, a body of magma that's 5 kilometers in volume can approximately reproduce the explosive yields that were measured to produce that giant land wave. And it doesn't really matter what proportion of water you involve. So we've got our 20%, 40%, and this is 80% water in our phreatomagmatic mixture. That's what those different lines are. It doesn't really matter how much water you put in there. You can still make this eruption using those proportions of water. Right. So then I wanted to vary, okay, I feel pretty comfortable with 5 cubic kilometers. It's a reasonably kind of in the middle on efficiency. It's kind of in the middle on water. Works if you think about, okay, well, we can't have any more than 6.3 cubic kilometers involved. And the volcano continued to erupt after this really big explosion. There was still 6 more hours of eruptive activity after the really big peak plume. So all of the magma can't have come out at once. You still have to have some volume left over in the system to come out. And that's why I feel that 5 cubic kilometers is a good magma volume. That maybe this was the volume that was needed to put that ash 58 kilometers into the air. And then maybe another cubic kilometer continued to erupt out during the remainder of the eruption. So for this model, we wanted to take a look at proportions of water and also make sure that we could constrain the depth to our magma storage. And to constrain the proportions of water, we did calculate the exit temperature at the time of the eruption. Anything beneath 400 C is just unrealistic. So again, for a very large magma body or something very, very deep, we can't have a lot of water. The exit temperature, the modeled exit temperature isn't real. But if we have our vent at, again, about 2 kilometers in depth, we can reproduce the explosive yield seen. So yeah, that's pretty much what we're concluding. We're estimating that we're on the order of magnitude of 10 to the 12th kilograms of seawater that was put into the eruptive plume, that there was approximately 5 cubic kilometers of magma that was needed to make the 58 kilometer plume that was erupted and involved in that explosion, and that magma was stored about 2 kilometers depth immediately before it was propelled 58 kilometers height. And yeah. So I'll take any other questions you guys have at this time, and thank you so much. I hope you enjoyed it. Again, be kind, not a physicist. Yes, sir.
Do we know when we get a guesstimate? It's like seismic activity, like nearby surrounding area. Or does it even matter nearby area considering seismic activity has effects on other sides like the ocean, I guess, in a way?
Well, it only is going to have that big of an effect on the ocean in this big of an eruption, honest to God. You cannot predict a volcanic eruption, and that's because a prediction implies a time, a place, and a magnitude. You can only forecast them. Forecasting usually does involve seismic activity because volcanic earthquakes give off a very specific seismic signature that's different from a tectonic one. But you would need to have at least 3 seismometers close to the volcano. You would also need to already have a good understanding of how that volcano behaves and what signals it gives off during eruptions. So that's why, like, what I do is I study individual past eruptions to try to glean that information so that when the volcano does become active again, we know where the magma system is and things like that. That's a great question. I'm also totally open to collaborations. Again, simplified model, not a physicist, but if you guys are into volcanoes, they're pretty dang cool. All right. Yes.
Trying to figure out the explosive push on the atmosphere.
Uh-huh.
That happen. And what is you had that integral P delta V that and the integral P delta V and thinking of pressures that are associated with the magma, but also how fast did the water, any seawater that was in contact with a high amount of heat, how fast did that, say, go from liquid to vapor? And so you end up with the pressure volume expansion just from water.
Well, and that's what this is kind of modeled. This is modeled as an isentropic process because we're assuming that it's happening at one pressure and it's just so instantaneously that you don't really have a difference in entropy. Does that answer your question? Probably not. I think we're just talking the same thing.
Yeah, just trying to think through it.
Oh, yeah. I'm happy to leave this with you. I'm happy to send you a copy of our manuscript too, as long as the co-authors are okay. I'd love to get your thoughts on it.
Yeah.
Yeah, for sure. Any other questions? Cool. Yes. Oh, I would imagine. When Mount St. Helens erupted, now that whole place is a natural lab, and biologists have, gone to see which, plants and animals come back first. So I believe that they have. I don't see why they wouldn't be.
So you mentioned that it's hard to predict when a volcano is going to pop. You showed that picture of the crew that had they been there the next day would have been dead. When you're that close to the volcano, are there ways to guesstimate how close is safe?
No. For example, like, Mount St. Helens, David Johnston was 13 miles north of the vent. And honest to God, the USGS didn't think that the lateral blast would go that far. They thought that it would only go maybe 6-7 miles. And he wouldn't have been there if he didn't think he was safe. We always put safety above all. So, but sometimes we're wrong.
Did those people that you showed the picture of the day before, they realize how much danger they put themselves in?
Yeah. Oh, yeah. But I mean, nobody saw the eruption the next day coming. That literally, those phenomenon, the last time that they were recorded was during the 1883 eruption of Krakatoa. So, well, they knew that it was a Plinian eruption, but they were far enough away to be safe. That is a safe enough distance to where they're at for a Plinian.
But like you were saying, they wouldn't have survived if they'd stayed there.
No, well, if they had been in that distance the next day, if they had been this distance away the next day, and that's because of the pressure wave. Yeah, but again, that's a phenomenon that nobody could have seen coming. And so it would have been kind of a similar David Johnston scenario as in yes, we thought we were good. Under normal conditions, this is but under normal conditions, this is what volcanologists would deem a safe distance for us doing a job. Emphasis on the professional job. But even then, we can be wrong.
Fortunately, we are going to have better and better drones that can go where we shouldn't go.
Yes. We are using that a lot. Volcanologists are, at least. Yeah.
reading it itself and collecting data from it, very difficult. I just like, it's pretty insane just to see all of this kind of brought at once. Because like I knew volcanoes were unpredictable beforehand, but I didn't realize how unpredictable.
Yeah, they're so cool. Yeah.
And then like city dates for
Mm-hmm.
like
There are. They're inconclusive. I think the strongest link is with elephants because elephants have some sense, they can sense energy in the ground. Um, that's as much as I know. I know that there has been no conclusive link. There's no definitive like this animal scurries in this pattern and that means this, you know, there's nothing like that. But yeah, there's loose correlations. I know it is a focus of study though. Yeah.
the Yellowstone wasn't that angry. So what thing?
Kilauea. Yeah. So hazardous, danger and hazard and risk is couple, it's not just explosivity. It's how many people live there. Rainier is number 2. Yeah, Rainier is number 2. Mount St. Helens is number 3. Rainier is number 2 because it's less monitored. And we actually don't.
Well, also
No.
potential. It has a potential of a whole lot of snowmelt real rapidly.
That's the bigger hazard. And that's the bigger hazard, yeah. Mm-hmm.
Go ahead.
Yeah, there are actually machine learning has been used for gosh, at least the past decade now to look at seismic predictions and we can't predict, but look at like trying to, I guess let me rephrase that. Trying to better identify smaller earthquakes so that we can maybe see signals quicker and like further into the future, further in advance, if that makes sense. But yeah. I can't say definitively, but it would likely not involve external seawater. So likely not, but I can't say, you know, I can never say no, but without external seawater, you're less likely. I'll leave it to Holger.
One last.
So the water is acting as like a catalyst.
Yeah. Yeah, yeah. Uh-huh.
Well, all right, we can continue informal discussions after, but let's thank Melissa one more time for an awesome talk.
Thank you.
Thanks to all of you for being here. Have a good winter break and see you in spring for the spring seminar series.